Good morning, everybody. Welcome to day 2 of this last week's workshop of our program. Once again, we have 2 talks in the morning, then a short coffee break, then 1 hour of discussion with the speakers, and then in the afternoon we have another panel session. We are starting off this day with Robert Brandenberger from McGill, who will tell us about emergent metric spacetime from the BFSS matrix model. The stage is yours.
Great. So first of all, I'd like to thank the organizers for putting together this workshop and obviously for inviting me to speak. So some of you have heard me speak about this research program or part of this research program before. It's actually, I consider this to be the most ambitious thing that I've ever done. But you see, it could be completely wrong. In fact, I learned the lesson from my de facto PhD advisor, Bill Press, with reference to a paper of his, which turned out to be wrong. He told me, if you want to do something new, you have to risk being wrong. So this is just a warning. I find this a very ambitious program, but there could be fatal flaws. Now, part of the program is actually very new. You are the first people to hear this part here. And I'm sitting on a paper which is ready to be posted to the archive, but I'm sort of interested in feedback. Okay, those of you who were at the discussion yesterday, they realized that I made some quite extreme comments, criticisms, specifically about inflation, and I'd also like to back them up a little bit. So I'm first of all going to talk about the Trans-Planckian censorship criterion, which basically means that standard inflation, treated as an effective field theory, is in trouble. Then I'll remind you that we don't need inflation to explain the data. There are alternatives. Okay, so this is all very solid, and I'll hope to convince everyone of that. So now, in all of the scenarios for early universe cosmology, we need a non-perturbative treatment. And so what I will be doing is I'll be trying to develop a non-perturbative approach, an emergent metric spacetime from a well-defined Lagrangian. It's a matrix model, BFSS matrix model, Banks, Fisher, Schenker, Susskind. This was a matrix model which was proposed in late 1996 as a non-perturbative definition of superstring theory. So what's new is I'll be trying to get an emergent metric spacetime and also an early universe cosmology from it. And the space that emerges will have precisely 3 large dimensions, which naturally you know all about, Mary, because that's exactly what happened in string gas cosmology. And actually what will happen here is it's the embedding of this old string gas mechanism that distinguishes 3 dimensions. It's the embedding of that into matrix theory. So this is the menu for this morning. Good. So, okay. So current early universe models are based on effective point particle quantum field theories. And already the fact that there are singularities should tell us that there's something wrong. And it should, as you heard in talks yesterday, one of the goals of quantum gravity is to resolve the singularities, in particular the cosmological singularity. Now, I will be working under the, I'll be basing my analysis on superstring theory as a candidate for a quantum theory of all forces. Now, again, I'm not a string theorist, but I think I've been persuaded that string theory is the best candidate in town for a unified quantum theory of all forces. So, okay, again, since I'm not a string theorist, I will not be able to defend this point very strongly. I will take this as my starting point and see what follows from it. So the question that I'll be asking is, can superstring theory resolve a cosmological singularity and give us some nice cosmology without a cosmological constant? Okay, so now for those of you who partied too late last night and will want to take a morning rest, here's a preview. So we need a non-perturbative approach if we want to do all these good things of remove singularities, get an early universe cosmology. And so my starting point is a particular starting point. And I think this starting point has a lot in common with what you are talking about, Daniele. So I think there are close connections. Stefano, I'm always mixing you up. I did it once before. You know, there are too many Italians, so not enough different names. I apologize. Okay, so so I will try to show. I will show that using this starting point, we get an emergent metric space-time element of universe cosmology. Okay, so here is my criticism, my argument why you have to go beyond point-particle effective field theory. So this is a slide which I showed more than 20 years ago this is work with Jérôme Martin. We called it the Trans-Planckian problem for inflationary cosmology. So here's a space-time sketch of inflation. Time is the vertical axis, physical space is the horizontal axis. The time between Ti and Tr, that's the period of inflation. And in inflationary cosmology, treated as an effective field theory, there is a Big Bang singularity. And now there are these three length scales. There's the horizon, which expands exponentially during inflation. There's the Hubble radius, which is constant during inflation. The role of the Hubble radius relates to cosmological perturbations, which carry most of the information about data. So cosmological perturbations oscillate. If the wavelength is smaller than the Hubble radius, they freeze out and are squeezed on scales larger than the Hubble radius. That's the important role that this Hubble radius plays. And the red curve, that's the physical wavelength that corresponds to scales that we observe today. For example, the scales that we observe in the cosmic microwave background. So the success of inflation is that at early times, scales that we observe today are smaller than the Hubble radius, so we can imagine a mechanism that moves matter around, creates fluctuations. The problem is that if inflation lasts only a little bit longer than the minimal time that it has to last in order to be successful, in order to explain the overall isotropy of the microwave background, then the length scales that we observe today are smaller than the Planck lengths at the beginning of inflation. And they are in this zone of ignorance where we know that standard point particle effective field theory breaks down. Okay, so when I presented this slide in 2019 at the summer workshop at the Simons Center, workshop organized by Waffer, the day after my talk, Waffer walks into my office and says, this is a new principle. This is the Trans-Planckian censorship principle, censorship criterion. It says, yeah, this depends on the energy scale of inflation. If you take grand unified energy scale, then you need 60 E-foldings. And if you have more than 70, you have a problem. Yeah, then you have this problem. So staying below what? No, you don't avoid the problem. You avoid the problem the way that I formulated it now, but you don't avoid the problem as I will formulate it now. So according to the previous slide, yes, there's a window where you're safe. I will argue that you're not safe. Okay, so the Trans-Planckian censorship criterion says that in no theory, which is consistent with quantum gravity, scales that classicalize can ever emerge from the Trans-Planckian region. So if we take the usual spatially flat Friedmann metric, it means that if you start at any early time, any initial time t sub I with the Planck length, you let that scale evolve to any later time, you have to remain smaller than the Hubble radius at that later time. So this is a trans-Planckian censorship criterion. And now I will give 3 justifications for this. None of these are specific to string theory. Okay, good. So the first is an analogy with Penrose's black hole cosmic censorship hypothesis. So here's a space-time sketch of a black hole with charge Q smaller than the mass. We are an observer far away from the center of the black hole, and there's some bad stuff happening at the center, but we are shielded from this by the horizon. Now, Einstein gravity, as an effective theory, admits solutions with charge greater than the mass. Now, in this case, the poor observer far away from the black hole is not shielded from the bad stuff. So what Penrose postulates is that in any theory, in any ultraviolet complete theory, the external observer must be shielded from the singularity and associated non-unitarity by a horizon. So this is Penrose, the famous conjecture. And now let's translate that from black hole physics to cosmology according to this translation scheme. Position space for black holes becomes momentum space for cosmology. The singularity for black holes is the trans-Planckian sea of modes for cosmology. I will replace the black hole horizon by the Hubble horizon. It's a very conservative choice. And then Penrose translated means that an observer measuring super Hubble horizon modes must be shielded from the trans-Planckian modes, which is precisely the trans-Planckian censorship criteria. So this is number 1. And the reason why I'm taking the Hubble horizon is that I want classical stuff, classicalized fluctuations to be shielded. Now, I don't mind if you want to make a stronger version of this criteria. I consider this to be a very mild criterion. So, okay, this is number 1. Number 2 is a unitarity problem. So there's an old paper by Nathan Weiss, who was professor at UBC, and he studied the non-unitarity of an effective field theory in an expanding universe. There's a recent paper by Jordan Cutler and Andy Strominger which resurrects this argument. So now by effective point particle theory, I mean a theory where you take all fields, you expand all fields in Fourier modes, and you quantize each Fourier mode like a harmonic oscillator. That's what I mean by a point particle effective field theory. In order to make this well-defined, to shield it from the Planck catastrophe, you need an ultraviolet cutoff, and it has to be cut off at a fixed physical scale. Now, to maintain this fixed physical scale in an expanding universe, you have to continuously create modes, which is this extreme non-unitarity. And so if you demand that classical fluctuations, things that classicalize, are insensitive to the non-unitarity, then you get precisely the trans-Planckian censorship criterion. Okay, now a side comment on this is that it is precisely this effective field theory approach to quantizing a system which gives rise to the quantum cosmological constant problem. Because if we use effective field theory, each harmonic oscillator mode has a ground state energy. That's a cosmological constant problem. So if the right way to do quantum gravity does not involve quantizing harmonic oscillators, the cosmological constant problem, the quantum aspect, goes out of the window. And you will see that in the model that I present, there is no cosmological constant. So that goes back to what you said in your model. There are some coupling constants in the model that I will present, but they do not affect this late time value of the cosmological constant, which is 0. Okay, so this is a side remark. Now, the weakest argument in support of the trans-Planckian censorship conjecture is something which is used all the time in black hole physics. People talk a lot about entanglement entropy between stuff inside and outside of the horizon. Well, let's do the same thing for cosmology. We can compute the entanglement entropy between sub-Hubble modes and super-Hubble modes. That's the analogy to what people do in black hole physics. in an accelerating universe, the phase space of super Hubble mode is growing. The entanglement entropy density grows. And if we demand that the entanglement entropy density at the end of the phase of acceleration is smaller than the entropy, than the thermal entropy that we want at the beginning of the standard Big Bang phase of cosmology, then we find that this phase of accelerated expansion can not last longer than the trans-Planckian centrism time. So see, all of these none of these three arguments involve string theory. They're quite general. Okay. Now, there are also connections with string theory. So what does this imply for inflation? So this is my space-time diagram of inflation again, the period of inflation, post-inflation. This is the Hubble horizon, and this is the Planck length. So now we want, there's an upper bound on the duration of inflation, which comes from demanding that the Planck length at the initial time doesn't become larger than the Hubble horizon at the end of inflation. So I drew this as marginally satisfied here. Now, if inflation is to be successful at giving us an explanation for the origin of structure, then the current Hubble horizon has to start out inside of the Hubble horizon at the beginning of inflation. I drew this as marginally satisfied in this space-time diagram. So now you see that whether these two criterion, this lower bound on the duration of inflation, upper bound on the duration of inflation, whether these are consistent or not, depends on where this scale is relative to the Planck length. The lower the energy scale of inflation, the further out you are, and that comes back to your question. So the less inflation, the easier it is to make these consistent. So there's obviously a simple calculation you can do. Here it is sketched. The upper bound on the duration of inflation from the TCC, the lower bound coming from demanding that the current Hubble horizon is inside of the Hubble horizon at the beginning of inflation. And you see that what you get is that the energy scale of inflation has to be less than about 3 times 10 to the 9 GeV. I'm a pencil and paper theorist, so take this 3 as an order of magnitude. Okay, now this means that we have to struggle very hard to get the amplitude of cosmological perturbations to be high enough. Completely unnatural. If we manage to do that, we get this following prediction for the tensor to scalar ratio, R, amplitude of gravitational waves divided by amplitude of cosmological perturbations, small than 10 to the minus 30. Secondary tensors will be larger. So please do not ever say that detecting B-mode polarization is a smoking gun of inflation. Absolutely false. And actually, I wrote a paper about 10 years ago with a title, "Is B-mode polarization the holy grail of inflation?" ? Okay, now the TCC has implications for dark energy. It implies that dark energy cannot be a bare cosmological constant, because if it were, sometime in the future, modes which today are Planck scale will be larger than the Hubble radius. And there are also constraints on dark energy. Okay. There, I mean, just a cosmological constant. Yeah. Yeah, I would say that this rules out inflation based on an effective field theory. Okay, but this is obviously a provocative comment. So you have to buy the TCC. Okay, good. But now, okay, I hope to argue that inflation is in trouble. If we want inflation, we have to go beyond effective field theory. Okay, now, do we need inflation? The answer is no. There are good alternatives. We want to explain this data. These are the amplitude of anisotropies of the cosmic microwave background as a function of angular scale. So Okay, so the data, the old COBE data, is the black dots with the statistical errors and systematic uncertainty. Now the data is much better. And then there's an artist who was given 6 parameters and was asked to fit the data with these freedom of 6 parameters. And these are 6 late time cosmology parameters. And this is the red curve which the artist drew. Now, the artists who drew this curve, they actually predicted this curve. And these artists are Zeldovich and Zunyaev and Peebles and Yu, 1969, 1970, 10 years before inflation. This is a sketch of the paper of Zeldovich and Zunyaev. So, co-moving length scale, time, here, T recombination, and so Zeldovich and Zunyaev assumed that there are fluctuations on all scales, including super Hubble scales in the early universe. Plane wave perturbations with a roughly scale invariant spectrum. That was the assumption. And roughly scale invariant was already known on theoretical grounds to be something which is good for data. Okay, now, but these fluctuations start to oscillate when the length scale becomes equal to the Hubble horizon. And you see that the length scale that enters the Hubble radius right at recombination doesn't have any time to oscillate. We catch it at maximal amplitude. The wavelength, which has done 5/4 of an oscillation, we catch it at a time where the amplitude is even, where there's only a velocity perturbation, and so on. So it is this sketch here which leads you precisely to these acoustic oscillations in the CMB angular power spectrum. So the physics that gives rise to these nice oscillations was well understood 10 years before inflation. So no way is this observation first prediction of inflation. Now, what Peebles and Yu and Zeldovich and Zunyaev did not know is how do you get these perturbations, which from the point of view of standard Big Bang cosmology are acausal. And this is where inflation came in. Inflation is the first, but not the only scenario in which you can get such a spectrum of fluctuations. So now there are a couple of graduate students here. And so that here I have the criteria that your quantum gravity model has to satisfy in order to be able to fit the data. So in your quantum gravity model, the horizon, causal horizon, forward light cone of a point on the initial Cauchy surface, has to be much bigger than the Hubble radius today. Otherwise, we can't explain the overall isotropy of a microwave background. Criteria number 2, scales that we observe today have to start out at some point in the past sub-Hubble. Otherwise, we can't locally move around stuff to produce the fluctuations. And finally, we also have to have a mechanism to produce scaling invariance. And indeed, inflation, the inflationary scenario, realizes these 3 criteria. The horizon is exponentially larger than the Hubble radius. Fluctuations start out sub-Hubble. And the fact that you have constant energy density during inflation, that explains why we get a roughly scale invariant spectrum of fluctuations. An old argument by Bill Press, not very well known. But in bouncing cosmologies, you can also realize these 3 criteria. So scale factor in a bouncing cosmology, there's a new physics that we'll hear about. There are several ways to get that. You'll tell us about one way to get that, Francesca. So scale factor is a function of time, bounce point. This is a space-time sketch. Hubble radius. The Hubble radius is decreasing the pre-Big Bang phase. In post-Big Bang phase, it's increasing. So time runs from minus infinity to plus infinity. The horizon is infinite. If you take scales back into the past, they start out sub-Hubble, criterion 2 satisfied. And I'll just make the statement that there are classes of bouncing models where if you start out with initial vacuum fluctuations, you can get scale invariant fluctuations right before the bounce. Not all bouncing models have that, in the same way that not all accelerating cosmologies give rise to scale invariant spectra. Now, the scenario which is relevant for what I'm going to talk about is the emergent scenario, which classically can be viewed as this evolution of a scale factor. There's an emergent phase where geometry might not make sense, a phase transition to the standard Big Bang phase of expansion. The resulting space-time diagram is this one. Emergent phase, H is 0 in the emergent phase. So this is the physical length of fluctuations. So you see the horizon is infinite. Scales start out sub-Hubble. A causal mechanism is for generating fluctuations is possible. And then the statement is that if you have thermal fluctuations in this emergent phase with holographic scaling, then you get scale invariant perturbations at late times, and I will show that later on. Okay, so I mean that quantities like the specific heat capacity grow as area, not as volume. And that's what emerges naturally from these string theory models. Okay, now to get a bouncing cosmology, you have to go beyond point particle effective field theory, because you need to get the bounce. You know, with Einstein gravity coupled to regular matter, you will never get an emergent phase. So we know that we have to go beyond the standard tools to get bouncing and emergent cosmologies. But I argue that also for inflation, you have to go beyond the standard tools. So bottom line is that all early universe scenarios require going beyond effective field theory. Now, Stefano, since you asked a question about holographic scaling, let me briefly review string gas cosmology. String gas cosmology is a toy model of cosmology based on some principles of string theory. So we postulate that there is a background space-time, and that space is toroidal in all 9 spatial dimensions, and that the space is filled by a gas of strings, a gas of closed strings, not a gas of point particles. And what we want to do is we want to use the key new degrees of freedom that distinguish strings from point particles, which are the fact that strings have oscillatory and winding modes. The fact that strings have oscillatory modes leads to the fact that there's a maximal temperature for a gas of closed strings in thermal equilibrium. And the fact that their winding mode leads to a new symmetry. Physics at large sizes of a torus is equivalent to physics at small sizes of a torus. Okay, I'll skip this. Okay, so if you take a box of strings with radius r, I plot it in string units, and you have thermal equilibrium, you plot the temperature. This is what the temperature does. If you start here, the temperature is in the momentum modes, because those are the light degrees of freedom. As the temperature increases towards the maximal temperature, the Hagedorn temperature, you can eventually excite the oscillatory modes. And once the radius goes below 1 in string units, then the energy will flow into the winding modes, the temperature will decrease. So this is the thermodynamics of a gas of closed strings. Now, from this, you might guess that the geometry will be a quasi-static phase. You live on this top of the hill for a long time, and eventually you'll roll off. Guess. So this, based on this guess, this is the motivation for what the scale factor does. And now this transition is, so if you take space wrapped by strings, then the space cannot expand. The strings will prevent it from expanding, because expanding space, these strings have to gain energy. So you can only have a transition, the scale factor can only start to grow if strings winding the space, if they can annihilate. And if long-range forces between the strings, then you can only liberate 3 dimensions of space, because string world sheets have 0 section probability in higher dimensions. So it's a problem. Okay. Good. Right. So if there are no long-range forces between two winding strings, then the windings cannot disappear unless the world sheets intersect. So what you have, maybe I have this sketch. No. So there is a board here. Okay, so this is my toroidal space. I start out with winding strings. I need to get rid of these windings, and this happens by this going into loops. So this is a process that gives rise to the decay of the string windings, and this requires the string world sheets to overlap. And if there are no long-range forces between two parallel strings, it means that this can only happen in 3 large dimensions. In fact, Mary did simulations of this and showing that indeed, if you do simulations in 5 dimensions, then you don't get space to expand. Yeah, 3 spatial dimensions. Okay, that's it. Good. Okay, so this is what is stated here. Good. So the conclusion of this part of the talk is that we do not need inflation. There are other, there are other setup. So good. Good. So this is the space-time diagram that we get. And now I want to show some equations which show that if you have thermal fluctuations of strings in this phase, you get scalar invariant spectra of cosmological perturbations and gravitational waves. So here, this is important, this slide. This is the method that we use to do the computations. So it's a 3-step procedure. We take the matter fluctuations in this phase. We know the partition function of the system, the final temperature partition function, so we can compute all correlation functions in this phase. Now, step number 2 is when a particular length scale crosses the Hubble radius, we convert the matter fluctuations to metric fluctuations using the linearized Einstein equations. So here, there's a connection to what you said, Stefano, yesterday about the underlying microphysics and the superlayer. So here, what I will be doing, I will be taking a particular microphysics and I'm converting it to the cosmological perturbations that's a slightly higher level. All that's important to get the conclusions is this holographic scaling, which I will show in this particular microscopic model. Okay, so step number 2, and then we evolve the fluctuations in the standard Big Bang phase like we always do, solving the linearized Einstein equation. So this is a 3-step procedure. So I want this to be clear because I'll rush through the equations. Okay. Good. So this is the metric of space-time, including cosmological fluctuations and gravitational waves. So the red stuff depends on space and time. The blue is the space-independent background. So the linearized Einstein constraint equations tell us that the cosmological perturbations are given by the energy density fluctuations. The gravitational waves are given by the off-diagonal pressure fluctuations. So here I didn't write I not equal to J. So now, since we have the partition function of a gas of strings in thermal equilibrium, we can compute this, and we can compute this. That gives us the cosmological perturbations and the gravitational waves. Okay. So this is now where the holographic scaling will enter. So in general, the energy density perturbations are given by the specific heat capacity. And for gas of strings in thermal equilibrium, this is the holographic scale of the specific heat capacity. R is the size of a box. String length. This is the temperature. When you do this conversion, this is the Hagedorn temperature. Okay, so we can compute the amplitude and slope of the spectrum of cosmological perturbations. Power spectrum of cosmological perturbations is given by this. And you see it's a function of k, and at first sight, it is independent of k. So at first sight, it looks like you get a completely scale-invariant spectrum of cosmological perturbations. But if you go back to this space-time diagram, you see that smaller scales exit the Hubble radius slightly later, when the temperature is very slightly lower. And this implies that you get a slight red tilt for the spectrum of cosmological perturbations, like in inflation.
How it creates the fact that when the temperature is equal to the Hubble temperature?
It never. If you take a gas of closed strings in thermal equilibrium, you never hit the Hagedorn temperature. You always remain below. How much below depends on the total entropy of the system. Good question. Okay. So let's go on and compute the power spectrum of gravitational waves. Now, if you look at the power spectrum of gravitational waves, this term 1 minus T over TH is in the numerator, not in the denominator. And it is this term which is giving you the tilt. And so you see that you get an opposite tilt for the spectrum of gravitational waves compared to the spectrum of cosmological perturbations. Yeah. So here I'm using the finite temperature partition function to compute these matter correlation functions. That's right. You never, but you see the Hagedorn phase is quasi-static. So it's a fairly good. On all the scales where I'm doing this calculation, I'm justified in doing it, at least at an order of magnitude level. Okay. If you go to the running of the spectrum, I think you'll have to be a bit more careful. Okay, so now you see that we have a prediction with which this quantum gravity scenario can be distinguished from usual inflation, because unlike for inflation, where you generically get a red tilt, here you get a blue tilt. And in fact, we get exactly the consistency relation between the tensor tilt and the scalar tilt, which I mentioned yesterday, which will come later in the talk. Okay, this is string gas cosmology. But the Achilles heel of string gas cosmology is we put in the space-time by hand, and we have no dynamics for the Hagedorn phase. If we use Einstein equations, we have a high density. We won't get a static universe. This is the Achilles heel of string gas cosmology. So let's try to do better. And I need water so that my voice recovers. And also now I'm going to on shaky grounds. Okay. So this may be wrong. I think it's very exciting, but just a warning, it may be wrong. Okay, so the starting point is okay. We are taking a matrix model, and I'll give you the Lagrangian next slide. And it was proposed in 1996 as a non-perturbative definition of M theory. It's a quantum mechanical model of D plus 1, where D is a number of spatial dimensions and D is 9 plus 1, n by n Hermitian matrices, where n goes to infinity. So there's no space. And it was motivated because if you do perturbative calculations of things that look like gravitons in this matrix model, you get the same result as if you do graviton scattering in this effective field theory 11-dimensional supergravity. So that was the motivation. I'm just going to take this as a starting point. So xi on 9 n by... Well, since there's no space. Yeah, by definition. Right, by definition. I just wanted... Right. There's nothing deep there. Okay, so this is the Lagrangian. G is a coupling constant, and we're taking the 12th limit. So n will go to infinity with this fix. Now, there's T is this is a quantum mechanical model. There's time. This is time. And it's written capital DT because capital DT is something that looks like a covariant derivative. It involves a 10th matrix. So the DT if A is a matrix, ooh. It is this. It's important. There's another matrix that arises here, an X naught. So we have 10 n by n matrices. We have an eta mu nu symbol in this Lagrangian. So what will not be emergent is local Lorentz invariance. Local Lorentz invariance is stuck in this Lagrangian. Excuse me. LS? Fermions. Fermions. So we are taking a supersymmetric matrix model, and I'm just not writing down this term. And the fact that the matrix model is supersymmetric is going to be important for two things. Just because there's an eta mu nu symbol, you see there's xi x j square. So there's a spatial part of the metric here, and just the fact that there's a minus in the Lagrangian that effectively gives you the eta mu nu. See, I'm getting the curved spacetime out of it. I'm not coupling it to curved spacetime. I don't want to take this matrix model and couple it to an external spacetime. All I have is a Minkowski's thing. Okay, so you see, that's what Lee Smolin's reaction is. You are much too conservative. You're just taking this matrix model which someone else proposed. So yes, I admit your point. I'm conservative. I'm just taking this matrix model which someone else predicted, proposed for some reasons, and I'm seeing how you can get emergent spacing. Yep. I have no defense. This is what we're doing. Okay. Yeah. But you'll see what comes out. No. We are getting space-time because, yes. Yeah, wait a minute. See, we are taking this matrix model in a high temperature state where there's no more evolution. So we've lost the BFSS time. So we have to get emergent space and time. That's a new part. We are taking this matrix model. It's a well-defined Lagrangian. We pick a state. It's a high temperature state. Okay. Now, by high temperature, I mean so high that the action is dominated by the Matsubar zero modes. So in a high temperature state, we can expand all matrices into their Matsubar modes. We get to the action, and then we choose a temperature so large that the action is dominated by Matsubar zero modes. Yeah, it's back. Okay, so now, good. So now the action of the Matsubar zero modes is the same as the IKKT action. This is an action proposed by these authors. It's a pure matrix model. There's no time. There's just an action and a partition function. So the action for the bosonic zero modes is this action. And there's a partition function. Okay. So now the idea is that we are taking these Matsubar zero modes, bosonic zero modes, and we are getting the emergent space time from them. And the other modes are the thermal fluctuations, which are giving us the cosmological perturbations and gravitational waves. That's the philosophy behind it. Okay, so these are all Hermitian matrices, so we can work in a basis in which one of the matrices is diagonal, and we choose the basis in which the temporal matrix is diagonal. And the diagonal values of the temporal matrix, those are the instances of time. And in the limit, when n goes to infinity, the size of the matrix, you can show that the maximal eigenvalue scales as square root of n, and the difference between eigenvalues goes as 1 over square root of n. So in the limit where capital N goes to infinity, we get infinite continuous time. Time runs from minus infinity to plus infinity because the eigenvalues are symmetric about 0. So this is not our work. This is work that was done in context of the IKKT model over many years. So now we also want to get space out of it. So the spatial matrices are not diagonal, but they have the properties that if you take if you look at the spatial matrices and you go away from the diagonal, then if you go sufficiently far away from the diagonal, where sufficiently far is quantified in this way, then the off-diagonal matrix elements decay away. So this and this you can show in the Lorentzian signature using the Riemann-Lebesgue lemma. And then numerically you can verify that if you are sufficiently close to the diagonal, the expectation value of these matrix elements are roughly constant. Okay. So these are features of these spatial matrices. Good. So now what we want to do is we want to define space at a particular time. And to do that, what we do is we pick our time from the temporal matrix. We go down the spatial matrices for the corresponding distance. We look at subblocks of the spatial matrices. And we call these subblocks at a particular time AI bar, where small n is the size of the subblocks. And then Nishimura and co-authors, they for a long time studied numerically the evolution of these quantities, expectation values of the trace of the subblock matrices square, which they call extent of space parameters. And they observed numerically that in a supersymmetric matrix model, there is spontaneous symmetry breaking, that only 3 of these extent of space parameters become large, the other 6 remain small. Okay, so now our proposal is to view the size of the submatrices Ni. Ni is the co-moving spatial coordinate. And the extent of space parameter is the physical length of a curve from n equals 0 to n. So this is co-moving coordinates. Extent of space parameter becomes length. If we have length, co-moving coordinates, we have the metric. So this is the way that we are getting emergent space. And this is the way that we are getting the emergent spatial metric out of it. This is the way that the metric emerges. Okay, now with the properties of the off-diagonal elements, which I showed you, you find that these GII components, that they are independent of the size of the submatrix. You find GII of Ni, E, is a function of T times delta II. SO3 symmetry, you get this. So what you're getting is you're getting an emergent spatially flat metric. And it is spatially flat out to a distance n sub c, which goes to infinity. So what we are getting now is we are getting an emergent infinite three-dimensional space, which is spatially flat. Okay, now why does this phase transition happen? What is the physical origin of this SO9 going to SO3 to SO6 symmetry breaking? So now I've always been under the impression that this has to be what Vath van Eyde discussed back in the old days, prehistoric days, before the archive. It has to be related to this picture here. So let's try to make this concrete. Okay, so to embed this old mechanism into this matrix model, we have to ask the question, where are the strings, or where are the D1 strings? So let's go back to field theory. I was forced to teach field theory 1 last year. So quantum field theory is a quantum theory of particles, but the particles are localized excitations of fields. So if this matrix model is a non-perturbative definition of string theory, the strings should be solitonic excitations of the matrices. So that's the idea. Let's see what we can do. So what are D1 strings in this matrix model? So the hypothesis is that D1 strings are solitonic matrix excitations, in analogy with how point particles are localized excitations of the fields. Now, the thermal initial state will contain all types of excitations, including these solitonic D1 string excitations. And so what we are going to do is we are going to take two parallel solitonic excitations, compute the force between the two, and show that in the supersymmetric model, the force vanishes. Free energy considerations will tell us that space cannot expand unless we get rid of the windings. This can only happen in 3 large spatial dimensions. And this is the embedding of this old mechanism into matrix theory. So this is the idea. So this is what we are trying to do. So what we have to do is we have to take the background configuration, which corresponds to our thermal back space-time, plus 2 parallel D1 strings. And we have to compute the one-loop effective action that you get for this ansatz. So we have to look. So this is our background. A mu B consists of this quantum background, which I discussed, A mu Q, plus the matrix configurations, which correspond to these 2 D1 strings. That's the A mu D1. And the A mu D1, that was actually proposed already by the authors of the IKKT paper. So to compute the one-loop effective action, we consider fluctuations about this background. The background is not supersymmetric, but in computing the effective action, we will consider all fluctuations, fermionic fluctuations and bosonic fluctuations. That's crucial. So the result is that the one-loop effective action for this ansatz is independent of the separation that we put in between these 2 D1 strings, which tells us that there's no force between these two D1 strings. Okay, so the way that the computation works is that this is the ansatz for the two parallel D1 strings. So A0, that's the temporal matrix. A1 is the direction in which these two D1 strings lie. A2 is the direction in which they are separated by distance b. So this is this ansatz which for a mu D1. So this we stick into the general expression for the one loop effective action for this matrix model. And then we find this result. Okay, so this is the proposed physical explanation for why in matrix theory you have this symmetry breaking. Okay, so now I have just a few minutes, and I'll just talk about the emergent cosmology. So I have to tell you about how this scale factor of the 3 dimensions evolves. Now, numerically, it's seen that it expands as g to some power. Low power, it is not accelerating. So our whole analysis never involves quantizing a harmonic oscillator. So therefore, it's completely natural that there's no quantum cosmological constant that arises. So there's no sign of a cosmological constant here. This can be obtained by solving the classical matrix equations in the 3 large dimensions. But we would like to do a more careful calculation of this. Okay, so now in this background, we have to compute the fluctuations. But we compute the fluctuations exactly the same way that we did in string gas cosmology. In string gas cosmology, we have a partition function, a thermal partition function. We compute partial derivatives. We get cosmological perturbations and gravitational waves. Here we have a thermal partition function. We do exactly the same calculations. So I can be quick. So see, this slide you already saw. In the context of string gas cosmology, we do the same calculations in the context of this matrix cosmology. The only difference is that we use a different partition function than the partition function that we get from matrix theory. So given the partition function, we have to compute the specific heat capacity through the energy partition function. Okay, so since this is a theory of strings, it is no surprise that what emerges is a scale invariant spectrum of curvature perturbations. It emerges from the calculations, but it's physically clear that this has to arise. What you see new, what we didn't see in string gas cosmology, is that there is a Poisson contribution on string scales, but that is also easy to understand. Gravitational waves are scale invariant. There's no Poisson contribution on UV scales. Okay, so what does our proposal give us, if it is correct? So the BFSS matrix model, which is a well-defined starting point, gives us an emergent infinite space, an emergent infinite time, an emergent spatially flat metric, 3 large spatial dimensions. It gives us thermal fluctuations with scale invariant spectra for cosmological perturbations and gravitational waves, and there's no cosmological constant. Okay, so I'm almost finished. There was a question. Okay. So obviously there's a huge amount of work. This is the beginning of a research program, and we have to show that we can get the Kepler problem right. So we have to show what kind of a low energy effective action emerges. So we have to do calculations more carefully. If we do calculations more carefully, we will get predictions for the spectral indices. At the end of this research program, we have to tackle dark energy. And here I believe that there's a new principle that will have to emerge, something related to the infrared ultraviolet correspondence. So it's the beginning of a research program. I find it very exciting. It could be wrong. And so these are the conclusions. So thanks for
Thanks a lot, Robert. We have time for maybe one quick question, I'm afraid. Who was first? Sorry.
Stefan was first.
Yeah.
Okay. Your calculation you're assuming that's classical GI rules.
Yes, absolutely.
So you have to prove that
On infrared scales. But remember, I need it on centimeter scales. Yeah.
Okay, in view of time, let's keep the questions for the discussion session and let's thank Robert again.
It's